So now we'll continue. We'll talk again about standard, but from local, national perspective. Let's welcome Csaba Huszty from Hungary, the owner of Intel Engineering and Consulting. The floor is yours, Csaba.
Thank you very much. It is a great honor to be here with you today. My name is Csaba Huszty, and I'm from Hungary, Budapest. I'm showing this video to architects when I go them to raise awareness about acoustics. In Hungary, we badly need the raise of this awareness, to be honest. I studied as an electrical engineer, and then I went to Japan, to Tokyo, where I did my PhD. I work as an acoustical consultant in Hungary, and we do some research and development as well in the field of artificial intelligence. And as a hobby, I play the pipe organ, but it's unrelated to today's talk. The motivation about creating a Hungarian standard on room acoustics was that we had various challenges. Among them, it is what I call acoustics as an option. I think everyone knows about this. When acoustics is neglected because of various reasons, including costs, nuisance, burdens, complication, limited awareness, confused priorities. So room acoustics was incidental in Hungary before the standard, and the building quality varied greatly. So we wanted to produce a reference for quality control and to overcome institutional actions which were actually lacking in Hungary. So I realized that important standards were missing, and I just got the phone and called the standardization office and said that we are a small enterprise and we need a standard. What should I do? 4 years later, we have a standard. But the Hungarian system, I think, is very similar to other countries. The laws are mandatory, standards are voluntary, and there is a third level, technical directives. This was added to the system of Hungarian laws because standards were actually pretty difficult to make. And this was a good side effect that some directives could help solving that. The application of standards, if we go back 80 years back in the history, was voluntary, and then there were 50 years when it was mandatory, and then 28 years. Since 28 years, since 1995, it's voluntary again. But the acoustic standards have been added to the decrees and laws so that it is mandatory, de facto mandatory again. This is very important. So the standardization in Hungary dates back to to the times where we were running on 2 horsepower cars. It was actually one of the oldest standardization offices in history. And since 1995, there is a separate institution dealing with the standards. Oh, and by the way, all the images here are a little bit weird because they were generated by artificial intelligence. The Hungarian Standards Institution is an open and independent legal entity. So it was really possible that an SME like us just went there, provided some finance, and the draft and the standard was initiated and created then. This kind of institution is very similar to what we have in Austria, Bulgaria, Croatia, Finland, Germany, and Switzerland, but it's slightly different from some other countries. In any case, any legal entity on a yearly fee can join the committee. There is no barrier of entry about knowledge. Even the grocery store manager can come and influence the room acoustic standard. Luckily, it didn't happen. But the delegates of the legal entities are all there on a voluntary basis. So anyone can do anything, and this results in a very interesting procedure. We have to produce a standard draft as an initial proposition, the financing, and the committee, the local committee, has to put the standard on the agenda. Consensus in theory, happens when 66% agrees and no more than 25% disagrees. This proved to be a very important figure in the voting process. For building acoustics, we already have standards since about 1972. The most current update for the building acoustics standard was on 2007, but there was no acoustics standard in Hungary for room acoustics, and nothing for open offices, and nothing for electroacoustics. So we thought that maybe we should do a national standard on room acoustics as well as electroacoustics, and later we adopted the 22955 standard. So actually there is one country where this is mandatory, and that is Hungary. So this image depicts quite representatively the process of creating the standard. It was a long story, but in short, there were attempts before to create a standard in Hungary for room acoustics, but they failed. The committee was actually not functional. There was no president on the committee, and nothing was happening there. There was no financing. The government was doing nothing, and there had to be done something. So we first created a draft based on the German standard, which was just released at that time, also considering BB93 and some of the Baltic standards. And I invited all acousticians in Hungary to participate in this process, all the 12 of them. So it was, even though we were just a small committee, it took 4 years, alternative drafts, internal meetings, committee dissolvement, voting issues, you name it. And from the requirements and the mandatory control, we designed the standard having limits instead of targets. Originally, we started with the German approach, but fellow acousticians didn't much like the idea. So instead of telling how acoustics should be, we ended up in a standard how acoustics should not be. But this is also very good, I think. We have basically two values, which is mandatory: reverberation time, averaged over frequency and space, and equivalent absorption area. And we also have STI as a recommendation only. This almost took my life to edit. And we still don't have G, D50 or C50, so there is still room for improvement. The usage of the standard is pretty simple. For each room, we define the function of the room, except for open offices where function could be multifold. We define the requirements according to the standards, and where the standard has no coverage, because, for example, we design a space station, which is not included in the standard, then the standard says that we should hire an acoustician to tell what values should be prescribed for that special case. And then the design of the room, materials, placements should be added, and compliance must be proven. So it's just not enough to sign the papers that it's going to be okay, I promise. You have to submit some calculations and documentation as well. And for schools, and this also almost took my life, we have mandatory measurements as well in the end. So this hopefully gives a little bit more guarantee that what is designed is going to actually happen. The values are mostly based on the Sabine equation, and similarly to the DIN standard. And just as an example, it has volume limitations, 0.7 unoccupied, furnished state, and for speech lab or some special cases, it's a little more strict. But there are many things to actually improve. So since the standard has been published, as I mentioned, we are very much into AI and the research related to that. So we tested whether the current international standard helps us or not to choose between methods of the Sabine equation or Odeon or other numerical simulations. So we created 30,000 rooms in Odeon and simulated them And you can see on the graphs the prediction of the Odeon T20 and the prediction of the Sabine formula, and the colors show the decision result, whether you should use the Sabine formula or not, based on the current EN standard. You can see that it's pretty much a 50-50 guess. It's giving a lot of false negatives. So it's really not very easy for an acoustical consultant at this moment to choose whether they can rely on the Sabine formula or should use more advanced methods. And this is particularly important in Hungary, where the market is made so that it is very difficult to convince the stakeholders to actually finance a more advanced calculation in the design process. But if we rely on the Sabine formula, we end up with over or under designing the space. And in terms of schools, for example, we have the test measurement mandatory happening. So if something goes wrong, then the acousticians are in trouble. So let's look at some other formulas. They can help us maybe, or maybe not. If you look at the other formulas, we're in even bigger trouble. The Sabine and Eyring equations almost give the same results. The Arau formula is a little bit better. The Fitzroy is not. So there are things to improve in the standard. One of them is the method, how to calculate reverberation time. And the other one is to include D50 or C50 or G or SPL. And basically, the reason why these were not yet included is because of the modeling methods. Also for the STI, we had feedback from fellow acoustical consultants that it really must be simple to calculate or predict these values. There should be a method which simply predicts these formulas for ordinary spaces. And we should not make our lives too difficult to make it mandatory to use modeling, which is actually very, very complicated and expensive. So that is the reason why we started our research in machine learning, whether we can combine the merits of more complex calculations and more accurate results. And I'm just showing just one single slide of that. So if you take just 2,000 samples from these rooms randomly, because we use the rest of the data to train the neural network, this is what you get for the Sabine prediction. The lines are 50% up and down from the target values. This is what you get from the Eyring equation. This is what you get from the Arau equations. And this is what you get from the EN standard. And this is what you get from the neural network. So it seems that it is possible, given the appropriate networks, that you can predict pretty similar to, for example, Odeon or any other reference values, assuming you have the amount of data, without the need of actually going into the computer modeling. And this can happen really fast. I mean, these calculations, the inference of neural networks is very fast. And this is basically, and maybe this is sounding a little bit weird, we are doing this research together with a Hungarian university called ELTE, with the mathematicians there. But we are using language models to predict the room conditions. And in the long term, this might result in a new scenario where you can describe the room with words and get room acoustic parameters. Thank you very much for your kind attention.